we proceed with the second lecture of the course, which is going to be about fermions. I see that the level of interaction which we have is really insufficient, at least for me. So I'm thinking maybe next lecture or lecture after the next, we either start with a little quiz, so you will be answering questions, or we finish lecture with a little quiz, because otherwise I don't have feeling that you are listening to me, really. And again, these are your lectures, and this is your way to get knowledge. So therefore, I hope very much that you are really working with me and not watching internet, not writing emails, not chatting with your friends on your cell phone, and so on and so forth. But I'm not going to check it. Again, this is your business. And please be responsible and please follow me. Okay, lecture number 2. Fermi gas and Fermi liquid. So let me recapitulate quickly what we have discussed last time. So we said that if we start with a non-interacting particles, today I'm only going to talk about fermions only. Then, based on the single particle wave function psi, which depends on psi and has index p I, which enumerates states which are solution of your single particle Schrödinger equation phi equal to E phi. So we construct the basis. Then there are two types of the many body wave function of non-interacting particles. One type of wave function corresponds to symmetric wave function, and this is describing the system of non-interacting bosons. Yet another type of wave function is fully antisymmetric function. I will call it psi. I put index fermions. It depends on coordinates and spins psi n. And it can be constructed with the help of the single particle wave functions as a determinant. Phi E1 psi 1, phi E1 psi 2, phi E1 psi n, phi E n psi 1, phi E n psi n, and there is a normalizing factor 1 the square root of n, factorial. So this is the wave function of n non-interacting fermions. And we had two important conclusions. First of all, if there is a pair, at least pair of quantum states, Pi is equal to Pj. So this is, for example, rho I, and this is rho j. If we have these quantum numbers are completely the same, then our wave function psi fermion is equal to 0. And this is a Pauli principle, which says that the fermions can occupy given quantum state with an occupation number either 0, no fermions, or 1 fermions. Two fermions cannot occupy the same quantum state, being characterized by the same set of quantum numbers. So this is because of two rows are identical, and Slater determinant, this is a Slater determinant, is equal to 0. However, we can also see that if psi I equal to psi j, so this is a column, well, let me say m and n, if we want to, so this is a column m, and this is a column n, then the determinant is also equal to 0. So psi f is also equal to 0, which means that two fermions, the wave function of many fermion state has a node in a position where two fermions share the same coordinate. Good. So this is a property of fermionic many particle wave function describing the system of non-interacting fermions in 3 dimensions. I'm very careful in everything what I'm saying because there are some situations, namely I mentioned quantum Hall effect, where, and this situation is very specific for a system of 2-dimensional gas, which is not going to be part of this first lecture. I will be back to the statement, but let me be very careful. Namely, we are talking about 3-dimensional situation of non-interacting, identical, indistinguishable fermions. So, then, what did we say is that the occupation of the state P and Fp is either 0 or 1. Nothing else. So then we have derived, using methods of statistical mechanics, the Thermionic distribution function. A Thermionic with the index k, and in principle sigma, which is 1 over e to the power epsilon k sigma minus mu divided by temperature plus 1. Again, in the previous lecture, I used the system of units, the Boltzmann constant equal to Planck constant is equal to 1. Which means I measure energy, temperature, and frequency in the same units. So, suppose that we are at 0 temperature. For the moment, I will assume that temperature equal to 0, so I'm discussing the ground state properties. Ground state. For illustration, let me take 1-dimensional well with infinite walls. Which describes 3 sphere particles. In particular, for illustration, I take 1-dimensional system. So the energy scales, so epsilon k sigma is equal to h squared k squared over 2m. Remember that I don't use h bar anymore, and if magnetic field B is equal to 0, we have twofold degenerate state. So, if I will draw energy levels, which square with quantum number n is n squared, so this is like that, and now in accordance with the Pauli principle, I'm going to put fermions on each level. As I said, at magnetic field equal to 0, each level is twofold degenerate. I can put 2 fermions with a spin up and down, and only 2, because these 2 fermions are characterized by different set of quantum number, at least one quantum number, namely projection of a spin to the quantization axis is different. So I keep putting, and so on and so forth, until I put everything, and the next level is empty. So there is energy until all states are filled in, and all states below that energy are filled in, and all states above are empty. For simplicity, I'm not going to discuss different situations, whether we have odd or even number of particles, because if you remember that we are dealing with a huge number of particles, 10 to the power 23, so it doesn't matter if we have a 10 to the power 23 or 10 to the power 23 plus 1. Therefore, I'm not going to discuss whether the last field level is half field or double field. Doesn't matter for me. For me, it's important that we have an energy below which all states are filled in and all states are above which the states are empty. Therefore, if we plot the distribution function as a function of energy, this is n f epsilon bar, so this is 1 and this is 0, so there is an energy which is actually, if you look at this equation, is a chemical potential, temperature equal to 0, below which the states are filled in with occupation equal to 1. So this is how Fermi distribution function looks like at 0 temperature. We are saying that the chemical potential, which is in principle function of temperature, at temperature equal to 0, we will call it, this is a definition, this is a Fermi energy. Therefore, as I say, all states below Fermi energy are filled in, and all states above Fermi energy are empty. So, if we are talking about realistic metals, how big the Fermi energy is? Well, the Fermi energy of metals, typical metals, is between 1 and 10 electron volts. So this is between, now I need to convert electron volts to Kelvin. I know how to do it. This is 10 to the 4, 10 to the 5 Kelvin. Is it big or not? For comparison, we can say that our room temperature, you know, it's about 300 Kelvin. So, 10 to the 2. The temperature in the crown of sun is of the order of, well, it's about 6,000 kelvins. So this is 10 to the 3, 10 to the 4 Kelvin. So you see that the question?
Yes, Professor. I want to ask about the 10 to the power of 5 and 4. Is it the Thermionic integral converted in what unit?
As I said, by this convention, the Boltzmann energy is Boltzmann constant is equal to h bar equal to 1. I need to convert electron volts into kelvins. So you can make all units dimensional, take into account Boltzmann constant. In principle, I'm talking about Fermi temperature. Let me be more explicit. So the Fermi temperature is obtained as Fermi energy is equal to Boltzmann constant times Fermi temperature. So this is a conversion unit. But I know the rule how to do it. I know what is also how to convert frequencies into the temperatures. So Fermi energy is h bar times omega Fermi, and therefore if I want to convert frequency to the temperature, I need to evoke both constant. But since I'm working in this field for many years, I know that 1 electron volt is approximately 10 to the 4 Kelvin. I know that 10 to the 11 Hertz is approximately 1 Kelvin. I can also convert magnetic field into the units of temperature or units of frequency. This is what we are going to do next lecture on Friday. But this is simple rule how to convert one unit into another. By this convention, as I said, I measure energy and temperature in the same unit. So I can say that my Fermi energy is 10 to the 4 Kelvin. So, all this exercise is done to say you that the gas of electrons, of non-interacting electrons, remains quantum, even at room temperature, because the room temperature is much smaller compared to Fermi energy. If you take your favorite program, mathematics or whatever, and you plot the Fermi distribution function for temperature, finite temperature, you will see that it will be modified in actually very narrow area. Of course, it will get tail, this is normal, but the area where you see the difference between the Fermi distribution function at zero temperature and Fermi distribution function at non-zero temperature is of the order of temperature. And what I'm saying is that at room temperature, this difference between in the Fermi distribution function at zero temperature, at finite temperature, is actually a measure of the temperature. And at room temperature, it is pretty small. We will use this fact when we will do our calculations. Okay? Yet another thing, I hope that at the end of this lecture I will be able to show you some realistic Fermi surfaces. We can define the surface below which, so let's go to the momentum state. So we have our energy P is equal to P squared over 2m. I remind you that P momentum is h bar k. Again, I will keep h bar sometimes, sometimes not. So what I plotted here, I plotted a surface that epsilon p, we have a quadratic dispersion, which is free particles equal to mu. And what we see that all states below this surface are filled in, and all states above this surface are empty. So this is a Fermi surface defined by simple equation. You take your dispersion, in our case it's P squared over 2m, and equate it with the chemical potential at zero temperature. Temperature equal to zero, which is, by the way, is Fermi. This is a ground state of ideal Fermi gas. However, the spectrum is not necessarily like that. If you take into account that you have a crystal, and in the course of electrons and phonons and solids, you discuss a different situation of a tight binding model and the different feelings, you need to plug in your spectrum, equate it with some constant, and you will get Fermi surface. What I plan to show you at the end of the lecture, if time permits, how realistic Fermi surfaces of realistic metals look like. So the approximation of free electron gas works good for some metals, but for some metals, of course, it's not true. However, all what I'm saying now for free electron gas can be one-to-one translated to the situation with a different shape of the Fermi surface. Okay? Is it clear? Good. I will proceed further. So, what we will do now, we actually derive one of the very important property of the Fermi gas, namely connection between Fermi energy and density of your fermions. Again, for everything what I'm going to do tomorrow, I'm considering three-dimensional gas of non-interacting fermions at zero magnetic field. Yeah, that's it. So, the total number of particles is equal to 2 times sum over P, and here we have N F bar P. Again, P is H bar K. Factor 2 is related to the degeneracy of our fermions with respect to projection of the spin of this quantum number, because we are considering zero magnetic field. Therefore, I don't put index sigma anymore. I took it into account, putting factor 2 in front. So since we have a system of many levels, we replace our summation over discrete levels by the integration in a standard way. So this is 2 times volume integral over momentum 2 pi h bar cube N P F. Okay, I am dealing with a zero temperature. Please. As I said, each level is twofold degenerate. When I relate the total number of electrons in my system with its density, I need to take summation of a level and summation of a spin projection. But since magnetic field is zero, each level accommodates 2 electrons. I put summation of a spin projection explicitly, it gives me a factor of 2. Okay? If we lift out this degeneracy at a finite magnetic field, this is what we are going to do Friday. We will behave and we will proceed with this summation in a different way. This is next lecture. Tomorrow, magnetic field equal to 0. So, if I assume that I'm dealing with ground state, temperature equal to 0, I will continue. This is sum over d over 2 pi h bar cube, and here I have a theta function over mu minus p squared over 2m. So, theta function is a step function which is 1 if the argument is positive and which is 0 if the argument is negative. Sometimes it is also called the Heaviside function. Now let me massage this equation a little bit. I already said that this is a sphere. The ground state is sphere for quadratic dispersion. Therefore, everything is isotropic. I can write down that element of volume dp is equal to solid angle 4 pi times p squared dp. Okay? So, therefore, I write it down as a 2 times 4 pi divided by 8 pi cube h bar cube. Now I do more. I would like to convert integration of a momentum by integration of an energy. So since EP is equal to P squared over 2m, it means that P is equal to 2mp. And therefore, this I can write down as 4 pi m divided by m p dp squared over 2m, and then I plug in this p. So this is m squared over 2m, and what remains here is integral from 0 to Fermi energy square root of epsilon d epsilon. So do you understand what I did? I changed the variables. Instead of variable p, I wrote down the variable e. Of course, I can proceed with integration in the momentum as well, but for some reasons I would like to go to so pi 8 we have square. The integral of square root of epsilon d epsilon gives me 2/3 e to the power 3/2. Therefore, I have my integral for n is equal to v, sorry, to turn off. Get it. Okay. L is equal to volume times mass times energy times square root over 2m energy, Fermi energy, Fermi energy. And I have pi square h cubed, and I have 2/3. Now I would like to introduce the Fermi momentum. So if I say that the Fermi energy and Fermi surface is defined by this equation, I can write down that the Fermi energy is 2 times square root over 2 times Fermi energy. This is a Fermi momentum, this is Fermi energy. If I write it down, I already achieved writing my connection between density and Fermi energy. If I continue this way, I will get mass is cancelled, factor of 2 is cancelled, Pf cube divided by 3 pi square h bar cube times volume. So what I obtain now that the Fermi momentum is equal to 3 pi square h bar cube n over d to the power 1/3. And this is very important because I'm saying that the connection between Fermi momentum and density is that the Fermi momentum, and Fermi momentum is nothing but the radius of the Fermi sphere, is related in three-dimensional system as a density to the power 1/3. Of course, the density is related to the energy as the energy, Fermi energy, to the power 3/2. Therefore, the Fermi energy is related to the density as n over v to the power 2/3. And it should be. Okay? And this is one of the central results of the Fermi gas, because this connection remains the same for the system of interacting fermions. We will see it when we proceed with this discussion of the Fermi. Okay? Is it clear what I did? I'm pretty sure you did this exercise in statistical mechanics, but I would like to repeat it because this is very important for many things which I'm going to discuss today. Okay, let's go further and discuss equation of state. And energy. So this was connection between Fermi momentum and density of states. Let's calculate energy. Energy of the system. So energy, with the same way of proceeding, energy is equal to 2 times sine over p epsilon p times NFP bar, where epsilon p is p squared over 2m. Then I will proceed with the same way of calculations. This is a 2. Factor comes out of degeneracy due to spin. Integral over d p over 2 pi h bar cube. Here I have p squared over 2m times NF bar. And again, I will assume the temperature is equal to 0. Therefore, I need to write down the volume. This is how I translate summation of a discrete state to the integration of a continuous state. So this is 2 times volume, and I proceed the very same way. 4 pi m square root over 2m divided by 8 pi cube h bar cube. This is what I wrote here. 2 solid angle and this factor and the denominator. And here I have integral to the Fermi energy. I'm talking about total energy, which is a thermodynamic potential, which is extensive quantity, which is proportional to the volume of the system of non-interacting fermions. So therefore I have epsilon times square root of epsilon d epsilon. So 1 epsilon is coming from here. Square root of epsilon has the same origin coming from the conversion of a momentum to the energies. So therefore this is epsilon to the power 3/2, and the integral is equal to 2/5 epsilon to the power 5. So therefore what I get is 2 4 pi square m square root of 2m epsilon Fermi to the power 5/2 divided by pi square h cube volume times 2/5. I can do the same as I did before, namely I can write m times square root over 2m epsilon Fermi. This is the Fermi momentum times pf squared over 2m. I therefore cancel mass here. I have yet another p squared Fermi over 2m, and I have pi squared h bar cube, and I have 2/5. So this 2 I cancel with this one. So as a result, I have pf cube over pi squared h bar cube times pf squared over 2m times 1/5 and volume. Pf cube is equal to this quantity. So what I have 3/5 volume times pf squared over 2m. Okay, I think I did not make any mistake. So I have 3/5 Fermi energy times volume. This is the energy of the ground state of non-interacting fermion. So energy per unit volume is equal to 3/5 Fermi energy. What I forgot here is actually no. this line is correct, and this line is not. Next line is not. So the Fermi momentum cube divided by pi square h bar is equal to 3 times n over v. Therefore, volume cancels out, and what I have here is not a volume but n, and therefore energy over n is equal to 3/5 of Fermi energy. However, I can also write down energy per unit volume. Energy per unit volume will be proportional to the n over v times Fermi energy, which is proportional to n over v to the power 2. So, therefore, energy per unit volume is proportional to the density to the power 5. Okay? So, this is proportional to the density to the power 5. Okay. This is all what I wanted to say about energy of the ground state. I was fighting for this factor 3/2 in order to prevent you naively doing that the energy of the ground state is the Fermi energy times number of particles. No. Okay? Let's compute equation of state. And this is, again, important. Of course, I can proceed with the same calculations at final temperature. No problem. This is what we will do on your first tutorial, which is going to be at the end of next week. And if you proceed with the energy, computing energy as a function of temperature, you will be able to subtract whole thermodynamics of your system, namely to compute specific heat, to compute entropy, everything you need to describe the thermodynamical state of your non-interacting many-body fermion system. Did you do it in your lectures of statistical mechanics? Or you didn't do it? Again, you don't answer, so I don't know. I take your answer as you didn't do it. So, equation of state. So, thermodynamic potential omega is equal to minus pressure times volume. So I would like to get equation similar to equation of Mendeleev and Clapeyron, which you discussed in statistical mechanics, where in the left-hand side you will get pressure times volume, and in the right-hand side you will get energy. So this is what I'm going to derive. In order to do it, I need to compute thermodynamic potential. Thermodynamic potential omega is minus is minus 2 sum over P. I have a temperature, and here I have log 1 plus E to the power mu minus epsilon P divided by temperature. So this equation we discussed last lecture when I introduced you to partition function and when I calculated the Fermi distribution function. So I need to calculate this. Again, factor of 2 coming from spin. I take summation of all quantum states. So it's equal to minus 2 volume and temperature, and I have integral dp over 2 pi h bar cube log 1 plus e to the power mu minus epsilon p over temperature. it is equal to minus 2 volume temperature times 4 pi. Everything is isotropic. I can convert my integration over momentum to integration over energy. M 2m epsilon divided by 8 pi cube h bar cube. And here I have integral from 0 to infinity, square root of epsilon d epsilon log 1 plus e to the power mu minus epsilon over temperature. I don't yet assume that I'm at 0 temperature. Here I did this assumption only to dramatically simplify my calculations. In principle, I don't need it. I can evaluate this integral under general conditions. So, I have quite complicated integral. And I would like to proceed computing it by parts. If we have integral u dv, it is equal to uv minus integral v du. Why I evaluate this integral by part? Because if I take a derivative of log, I will get the Fermi distribution function, which will then relate my integral to the integral which I have already calculated. So, therefore, this is d epsilon to the power 3/2 times 2/3. So this is dv, and this is u. So this is u, and this is dv. Therefore, my integral is equal to minus volume times temperature times m square root of 2m, sorry, here there is no epsilon, divided by pi square h cube, and here I have 2/3 uv, which is epsilon to the power 3/2 times log 1 plus e to the power mu minus epsilon over temperature minus integral v du. Integral 2/3. Integral from 0 to infinity. Epsilon to the power 3/2 times derivative of the log. This is 1 over 1 plus e to the power mu minus epsilon of temperature times e to the power mu minus epsilon over temperature times minus 1 over temperature. That's it. Okay, and here this is from 0 to infinity. Let's look at the first term. If energy is equal to 0, we have epsilon times log, and epsilon times log is 0. So the integral is 0 at the lower level, lower limit. If energy is equal to infinity, then we know from Fermi distribution function that the exponential factor is 0. We have log 1 is 0, therefore it is equal to 0. So this term doesn't matter. And as a result, I have minus and minus gives me plus. Temperature cancels out. And what we get at the end of the day is actually the same integral which we have here. The only difference is a factor of 2/3. Therefore, we have omega equal to minus 2/3 energy. So this is my equation of status. Yes?
I was concerned about the
I cannot understand what you are saying. Can you speak slower and what you don't understand?
Okay. I mean, integrity for the first two we consider 0 to be value, but now this one we consider 0 to be 1 point.
Because the Fermi distribution function for zero temperature is this. This is the Fermi energy, this is 1, this is 0. So it is step function. Epsilon n f epsilon. For zero temperature, I can put as a limit of my integration Fermi energy here. And this is what I did. And I explicitly said that this is zero temperature. If temperature is not zero, then we have exponential tail in our distribution function, which actually goes long to infinity. Therefore, if I'm at finite temperature, I need to integrate to the infinity, to the infinite energy. However, we evaluate this integral. This is what tutorial. I hope you did it in the statistical mechanics classes. There is a way to evaluate integrals with the Fermi distribution function, which actually says that there are corrections to thermodynamic potential associated with the finite temperature, which are T squared over Fermi energy squared. So, as long as temperature is small, the difference between result at zero temperature for thermodynamic potential at finite temperature is proportional to temperature square over Fermi energy square. As I said, in typical metals, temperature over Fermi energy, it's like 10 to the power minus 3. Temperature over Fermi energy squared is 10 to the power minus 6. We are discussing corrections to the main equation of the order of 10 to the power minus 6. However, if you need to evaluate the derivatives of the energy with respect to temperature, or derivative of free energy with respect to temperature, you need to take into account this first term. This, I hope, you did in statistical mechanics. If you didn't do it, I will ask my colleague on a tutorial next Friday to proceed with all calculations. He will learn how to deal with the calculations with the Fermi distribution function at finite temperatures, provided the temperatures are small. What happens if temperatures are large compared to Fermi energy? We discussed it on Monday. I said you that the limiting distribution for Fermi distribution function, as well as for Bose distribution function at very high temperature, is a Boltzmann distribution function. Then you just have exponential tail, and then you integrate with that. But you need to take into account that the chemical potential itself at finite temperature also depends on the temperature. So the chemical potential itself changes. It's a function of temperature. So you will do, if you didn't do this calculation before, you will do it with Andrei next Friday. And you see, here I related these integrals. In principle, I can write down the same integral here, infinity, Fermi distribution function, energy, d energy. The only difference is this. I replace a step function by two distribution functions, and this is precisely what I have here. Therefore, the connection which I found is exact at any temperatures, and this is what I'm going to discuss. This is a ground state energy, and this is total energy at given temperature. So, equation of states says pressure times volume is equal to 2/3 energy. Let me convince you that this equation is correct, and let's take classical limit. You remember, in the classical situation, if you have a gas of Boltzmann particles, then the energy is equal to 3/2 kBT times m. Right? This is a result from your Boltzmann gas. If you plug in this energy, classical to the equation of state which I derived. And this equation of state is varied both in quantum and in the classical limit. What you get, that P times V in classical is equal to K B T N. And this is Mendeleev-Clapeyron equation. Right? You see that my quantum equation in the classical limit satisfies known equation of state, which relates pressure, volume, temperature, and number of particles. Why I was spending some time to deriving this equation of state? In principle, you can derive similar equation of state for system of non-interacting bosons. This is what we will do in the first lecture of the chapter related to bosons. And believe me or not, we will obtain the very same equation of state. So pressure times volume is equal to 2/3 energy of the non-interacting bosons. Therefore, and not surprisingly, the classical limit will again give you equation of Mendeleev and Clapeyron. What then is interesting point? You can ask question, and this is what I'm going to give you as a sort of homework for those who would like to solve it. Suppose we have equation of state for fermions and bosons, which are true both in the classical and in the quantum limit. And in the classical limit, this both equation leads to Mendeleev-Clapeyron equation. In quantum limit, of course, they should be different because fermions are not bosons. So then, what you can do is to start with the classical limit and to calculate the correction to this equation, assuming that you are approaching the quantum limit. So you lower down the temperature. And therefore, you will get additional term which tells you how pressure in the system behaves when you deviate from the classical limit, branching either to fermions or to bosons. As a hint, I can tell you that in one case pressure increases and in another case pressure decreases. Therefore, and this is what experimentalists actually measure it in a very perfect way in the ultra-cold gases. So there is, so to say, statistical pressure. So when you start with the classical limit, it's very important whether you go in the direction of fermions or in the direction of bosons. So do this calculation and see which pressure increases and which decreases and how it is related to the Pauli principle. Okay? Good. Let me see what I did. We have some half an hour and I need to discuss two important... Yes?
Sorry to take you back, but I don't understand after the integral, like you just give like minus 2/3 of the energy that we calculated before.
Yeah. Because this integral which I have here is precisely this integral which I calculated for energy. Just for calculation of energy, I took at some point limit of zero temperature because I wanted to discuss the ground state energy. But if you proceed in a formal way and keep Fermi distribution equation, Fermi distribution function, you will see that this integral is identical to this integral.
I see.
So I relate my thermodynamic potential omega to another thermodynamic potential which is energy. And there is a factor of 2/3, minus 2/3. So, in a sense, I integrated by part, but I didn't complete this calculation because I would like to keep this result as exact at any given temperature. And this is true. and the equation of state is exact. But, as I said, when you took your Fermi or Bose distribution function and took a limit, so your Fermi distribution function is 1 over e to the power epsilon minus mu over temperature plus 1. We said that if this factor is huge, then we drop 1 and get it in the Boltzmann case as e to the power mu minus epsilon over temperature. So mu over temperature, chemical potential in the classical limit, is a large and negative. So this factor is small, so then it goes to Boltzmann distribution function, a to the minus epsilon over temperature. So this is a Boltzmann. However, I took only first term. You can took the second one. So you can find a correction to this Boltzmann distribution function, which will come with a different sign, because for Fermi distribution function here we have a plus, for Bose distribution function we have a minus. So this correction to the Boltzmann distribution function will be different for fermions and bosons with a different sign. And if you plug in, so in order to get Mendeleev-Clapeyron equation, you plug in this distribution function into calculations, you get Mendeleev-Clapeyron equation. However, if you now take into account correction, which depends whether you have a fermions or bosons, you will get a correction to Mendeleev-Clapeyron equation. And therefore, you can actually subtract additional, or people call it statistical pressure, which depends entirely on statistics of your system, whether you have fermions or whether you have bosons. Okay? Okay, I need to discuss, in remaining half an hour, I need to discuss two questions. Namely, how we go, what are the excitations and quasi-particles in the system of fermions, and how to actually convert the system of non-interacting fermions to system of interacting fermions. Okay. So first of all, this is a ground state. As I said, the ground state is a sphere. So all states below the surface of this sphere are filled in, and all states above are empty. If we now create the excitations, how can we create the excitation? We take a state inside sphere and put it outside. As a result, we create a hole. So this is a hole. So we have a hole inside n quasi-particle, which historically is called electron, outside. So now we have excitations which appear above the ground state. What is the energy of these excitations? Now we will count the energy of the excitations from the Fermi energy. So I'm saying that the energy of excitation psi p is p squared over 2m minus pf squared over 2m. So this is then modulus p minus pf modulus p plus pf divided by 2m. However, when I consider these excitations, I will consider them in the vicinity of the Fermi source. I will explain why in 5 minutes. So, this second term, namely modulus p plus pf, I can approximate as a twice of the Fermi moment. So therefore, I can write down that psi p, the energy of my excitations, is pf divided by m modulus p minus pf. Fermi momentum divided by mass is called Fermi velocity. Modulus P minus P. And what I see here is that my excitations of quasi-particles and whole course, which we are going to have about many-body physics, is about quasi-particles. We constructed ground state, we construct excitations, so the energy dependence on the momentum, which people call dispersion, is linear. Let me plot here psi p, which is epsilon p minus epsilon f. Since I shifted everything by Fermi energy, so this is minus Fermi energy. And this is modulus of the momentum. So I have a parabola. Right? I just took my parabola, p square over m, and shifted by Fermi energy. So this is then Fermi momentum. And what I'm talking about, this linear dependence on the momentum, which is sitting in this equation. So sometimes in literature, again, if momentum is larger than the Fermi momentum, these are electrons. If momentum is smaller than the Fermi momentum, these are holes. However, sometimes people use a different convention. They want to have both energies positive, therefore they reflect this piece of parabola, change a sign in the dispersion of hole, and saying that we have this linear dependence. We will use it when we discuss superconductivity, because superconductivity will then be related to opening gap at the Fermi momentum. But so far, we can say that this is energy of a quasi-particles electrons, defined as a positive quantity, and this is the energy of the quasi-particles which are whole, defined as negative energy. Now we have very legitimate question. When the quasi-particles are well defined, what is the condition? Suppose we take a wave packet. So we have our many-body system, and we take a wave packet out of this many-body state. So we are saying that...
Professor?
Yeah.
I have a question.
Yeah, please.
What do you mean by quasi-particle? Why it is quasi-particle?
I'm saying that quasi-particles and excitations are synonymous. So quasi-particles, quasi-particles are excitation. Why it is important? Because before we are talking about electrons as elementary particles. However, I'm going to show you that if we take, say, metal, some interacting Fermi system, we can still think about electrons, but not as elementary particles, but as excitations. Namely, we excite state from inner part of the Fermi surface to outer part of Fermi surface. We create, therefore, the excitation. And we call this excitation quasi-particle. Why quasi? Because it's different from the particle, elementary particle electron, and I will tell you how. Okay? But before saying what happens with interacting system, let me now address very important question, namely, when are we able to define quasi-particles? When the definition of quasi-particle is legitimate. Because I give you mathematically correct definition and give you example where this definition doesn't work. So it's not always that we can define fermionic excitation as true quasi-particles. But before I'm saying when it is correct and when it's not, I need to define mathematically what is the condition to for quasi-particles to happen. Okay? Okay.
Yes.
I'm saying that we take a many-body wave function subject to time-dependent Schrödinger equation is equal to h psi. So we create the wave package. So psi is then proportional to exponent I psi pi t. So this is a propagation of a wave packet. So this is, so to say, your wave mechanics, plane wave if you like, minus something which is related to decay of your wave package. So this is gamma p times t. So you create something, say Gaussian wave packet, and it propagates with the time. So in principle, it becomes broader and lower, broader and lower, and it disappears. Why it happens? Why it decays? Because we have interaction. So interaction actually makes this wave package to collapse. So therefore, there is something attributed to the energy of the quasi-particles. This is what I just defined. And there is something which is attributed to damping rate. Or decay of the quasi-particles. We can say that this gamma p is inverse lifetime of the quasi-particles. It has a dimension of inverse time, and the quasi-particles are well defined under condition that the energy of quasi-particles psi p is much larger compared to inverse damping rate. So this is a definition. We computed energy, and we see that it depends linearly on the deviation of the momentum from the Fermi momentum. In principle, after some lengthy calculations, I can show you that the inverse damping rate depends quadratically on the difference between momentum and Fermi momentum. Therefore, for Fermionic system, the quasi-particles are very well defined in the vicinity of the Fermi surface. Okay? Closer we to the Fermi surface, better our definition of quasi-particles is. This is for three-dimensional system of fermions. I'm now not referring to non-interacting fermions. Why? Because there is a brilliant theory known as Landau theory of Fermi liquid, which says that if we have a system with interaction, then it behaves in many ways similar to the system of non-interacting fermions. Namely, postulate number one, Fermi momentum is connected to the density of the particles in a unique way. So for three-dimensional, for example, this is to density to the power 1/4. Second, the dispersion of a quasi-particles now can be written as psi p is equal to pf divided by some effective mass and p minus pf. So we encode and encapsulate all effects of interaction into the parameter which is now called effective mass. We replace our zero mass as the mass of electron as elementary particle to the m star, which is dressed by the effect of interaction. Okay? By the way, if you remember your knowledge from electrons and phonons, when you have a tight binding model, so you have a hopping term. So you have a localized state, you have an overlap of the wave function, you have a hopping term, and if you want to expand your dispersion at small momentum, you will also have a quadratic dispersion. But your mass has nothing to do with the mass of electron, because it comes from the overlap of the wave function. It is related to the tunnel matrix element, overlap of the tails, and lattice spacing. So in principle, in solids, it's very seldom that the mass of excitation coincides with the mass of electron as elementary particle. So we are saying that first of all, the effects of interaction are encoded into the mass, and there is a second effect. We are saying that the distribution function for interacting fermions at zero temperature has a finite jump, which is called Z factor. For non-interacting fermions, this jump of distribution function at zero temperature is just equal to 1. For interacting fermions, we are saying that this Z factor is between 0 and 1, and all interactions in the system of interacting fermions are encoded in just two parameters, M star and Z. The rest is the same. Namely, we can treat interacting fermionic system as non-interacting ideal Fermi gas by replacing the mass by M star and replacing by the jump by Z factor, and that's it. And it allows to make a huge progress in calculation and explanation properties of the metals using the concept of Fermi limit. Okay. Hand-waving arguments why the damping is proportional to the energy square. It's very simple. Suppose we have a finite temperature in the system. Then we can say, first of all, the energy of the quasi-particle, how many such electrons and holes we excite, just depends on the temperature. I told you that there is a tail, and at finite temperature, the distribution function deviates from the ideal just in the window around the Fermi energy, and the width of this window is of the order of temperature. So the energy of the quasi-particle is of the order of temperature. The relative number of the quasi-particles which you create, relative number, is of the order of temperature of the Fermi energy. Therefore, gamma is of the order of energy times n, so this is of the order of temperature squared over Fermi energy. So the damping rate is proportional to temperature squared. And this is again very important property and hallmark of the Fermi liquid theory. Why it is so important? Because this is inverse damping rate. If you want to calculate the resistivity of the metal, and maybe we will have time to do it at the end of the course, we will relate the resistivity of the metal with inverse damping rate. So why this resistivity occurs? Because your electrons are scattered and put backwards. So the current is not running along the wire because the electrons are reflected and sent back. So you have a transport time, inverse transport time, which sends electrons backwards, and it creates sort of friction. And since friction is related to damping, this is the same as friction, in a sense. We can immediately conclude from this property that the resistivity of the metal will be proportional to temperature squared. And this is indeed true for all metals, and when there is a deviation of this law, I'm talking about those metals who do not become superconducting, say diamagnetic metals. These are therefore become exotic metals. So you see, from doing nothing, just estimating the damping rate of the quasi-particles, we can conclude how one of the important transport properties, like resistivity, behaves in the metal. Good. So, one technical comment about density of states, and I show you the Fermi surfaces. Okay? Some questions? I need to do something which I need for my next lecture, and namely introduce you to the concept of the density of states.
Professor?
Mm-hmm.
Hello?
Yeah, I'm listening, I'm here. Say me, tell me. Sorry?
Hello?
Yeah. What?
So, can I ask you why you define the energy of quasi-particle as the difference between the momentum and Fermi momentum? And also can you explain again a bit about the graph, of the parabolic graph you drew?
Okay. So, first of all, parabolic graph. I took my dispersion, which is p squared over 2m. And for the purposes which I explained you, namely, I would like to calculate the energy of the quasi-particle from the Fermi energy. So I need to shift my origin. Therefore, I took this parabola and subtract Fermi energy from it. So I put my parabola down. And now condition that I am on the Fermi surface tells me that I need to equate my momentum to the Fermi momentum. So, by the definition, energy at the momentum equal to Fermi momentum is equal to 0. So my origin now is at the Fermi surface. Okay? Now I'm calculating everything. Energy of the quasi-particle and the damping rate from the Fermi surface. Because, as I said, at the Fermi surface, or in quantum field theory, people say on a mass shell. On a mass shell, your excitation energy is equal to 0. Damping rate is also equal to 0. However, if you deviate from the mass shell, energy and the damping rate grow differently as a function of the difference between momentum and Fermi momentum, or energy and Fermi energy. As I said, quasi-particles are defined such a way that closer you to the mass shell or closer you are to the Fermi surface, better your definition of quasi-particles is. I promise to give you an example where it is not true. This concept of Fermi liquid works very well for three-dimensional metals, which are majority of the metals which we have in our nature. It works pretty well in quasi-two-dimensional metals, namely if you have a sort of films and a dimension in a perpendicular direction, thickness of this layer is much smaller compared to the size of the layer. So Fermi liquid is still perfect. However, if you are talking about quasi-one-dimensional systems, like wires, which are very important, by the way, for modern nanotechnology, then the concept of Fermi liquid breaks down completely. Namely, you can see that Z factor is exactly equal to 0. Namely, you don't have jump. And then, when you calculate the lifetime of interacting one-dimensional fermions, you will see that the lifetime is of the order of energy of quasi-particles. There is no smallness. Therefore, for one-dimensional system of interacting fermions, known as a Latinger liquid, the concept of Fermi liquid doesn't work. And the question, what are the quasi-particles in one-dimensional fermionic system? And the answer is that true quasi-particles are bosons. These are density-density fluctuations. And it makes a huge boost to the theory of one-dimensional system. The Managa-Latinger model, there was a bosonization, there was a beta-ansatz developed in. So one-dimensional system is where the concept of Fermi liquid breaks down. You have a Latinger liquid instead, and you cannot define the fermions as a true quasi-particles, and however, you can prove that true quasi-particles are bosons, like phonons, if you like. Okay? Density of states, which I will need if you had this definition or you didn't have. So density of states, nu as epsilon, by the definition is defined 2 times integral dt over 2 pi h bar cube, delta function of epsilon minus epsilon t. This is the definition. If we have quadratic dispersion, p squared over 2m, and we have a three-dimensional situation. So we can write down this is a 2 times 4 pi m square root over 2m divided by 8 pi cube h bar cube, integral from 0 to infinity, square root of epsilon, square root of e d e and delta function epsilon minus E. So the integral with the delta function can be taken in a very simple way. So this is m square root over 2m epsilon divided by pi squared h. So this is the density of states. If we plot this density of states for three-dimensional electron gas, let's do it here. Let's just make a plot, and then I can tell you the physical meaning of this density of states. So we are plotting the square root of epsilon. So this is density of states as a function of epsilon. And somewhere here we have a Fermi energy. So when we are going to discuss collective phenomena like superconductivity, like magnetism, it is very important to say that whatever we do, we are going to be in the very vicinity of the Fermi energy. So the Fermi energy, as I said, of the order of 10 to the power 4 Kelvin, corresponding magnetic field, for example, is going to be 10 to the power 4 Tesla. There are no, in the nature, so huge magnetic field except you make some nuclear explosion. In reality, in the lab, you can get a field of the order of 10 Tesla. So the same, if temperature, room temperature, is much smaller than the Fermi energy. So whatever you do in the very vicinity of the Fermi energy, and therefore people approximate the density of states by the constant, saying that nu at the Fermi energy is MPF divided by T squared H. So this is the density of states at the Fermi energy. What physically density of state is? You take the states from n to n plus dn with the energies from energy to energy plus d energy. And you can attribute your density of states nu as dn over d energy. So for three-dimensional gas, you have a square root. So where the square root comes from? You remember for fermions, Fermi energy is to proportional to n to the power 2/3. Therefore, n is proportional to the Fermi energy to the power 3/2. dn over d Fermi energy, we will get a square root. So this is the density of states, and by doing this, by applying this definition, it's very constructive to proceed with the calculations, expressing everything through the density of states of the electrons at the Fermi size. For those who are curious to do homework, consider two-dimensional electron gas. And in principle, in order to learn better what I did on today's lecture, please proceed with all calculations, assuming that you have a metallic film, so you have a two-dimensional electronic system. Therefore, you can find the density of states, you can relate Fermi momentum to the density. The relation will be different. As a hint, I can tell you that the Fermi energy will be proportional to the density to the first power, not to third. Therefore, the density of states as a derivative with respect to energy will be constant. So, those who would like to make exercises, do these calculations. Okay, and the last step, I would like to show typical Fermi surfaces. This is what I promised to do, and therefore I need to share my screen. Share. Do you see it? Do you see my screen? So, this is what I said. We have a fermions and the Fourier function antisymmetric. This is how for ideal Fermi gas we get the distribution function. These are excitations. For Lagrange theorem, I probably postpone it until the end of the lecture. This is potassium. This is lithium. These are Fermi surfaces divided by the condition epsilon P is equal to chemical potential, namely constant Fermi energy. This is calcium. This is magnesium. This is nickel. So you see that for alkali metals like lithium or potassium, you have almost spherical Fermi surface. However, when you go along the periodic table, the Fermi surfaces are very much different from, this is platinum. So sometimes Fermi surfaces have very exotic shape. This is a noble metal, platinum. Again, this is aluminum. The Fermi surface has several sheets. You have several bands. And in principle, take program of Mathematica, take any of your favorite spectrum in a tight banded model. Say, if you say that epsilon P is equal to 2 times T cosine Px plus cosine Py plus cosine Pz, equate it with a constant and plot the surfaces, take another dispersion, this is for simple cubic, take the dispersion for face centered, and play with this. You will get a lot of fun. So this is chromium and this is nickel. Why I'm showing you that? You see that for some cases like cobalt, the Fermi surface forms sort of cylinders, and these cylinders have a congruent parts. So these congruent parts of Fermi surface are called nesting, and the magnetism of cobalt, chromium, and nickel is associated with the congruent parts of Fermi surfaces. So we come back to this discussion at the end of your course. I'm done for today. Any questions? What did you write me in the chat? I told you that I'm not reading chat. To ask why we are in the denominator. Why can anyone read the question to Professor for me? Don't need to ask. Why we have two pH bar? Because this is how we proceed with the replacement of momentum to quasi-momentum. And this is, look, we have a system of discrete levels. Okay. I started with a quantum well, one-dimensional system. And if you have 10 to the power 23 particles, and your energy scales with the quantum number n for one-dimensional case is n squared, you see how many levels you need to get in order to accommodate 10 to the power 23 particles. And if we have so huge number of particles, we are saying that the difference between levels, which is attributed to this 2 pH bar, is much smaller, and we can replace summation of a discrete variable, which is a number of levels, by continuous integration of a quasi-momentum. This is how it is done, and this I think you learn in quantum mechanics, how to come from a summation of a discrete level in a system of large, big number of levels to the integration. And this is how H bar appears in this formula. Because your momentum is related to quasi-momentum through H bar, if you replace it by P by K, H bar is cancelled out. Okay?
Sorry, Professor. For the integral of density of state, we don't have V. Like
yeah, because we are not dealing with thermodynamic potential, this is not extensive quantities. This is per unit volume.
Okay.
More questions? Tell me, what did you have in statistical mechanics? Did you have this equation of state? Well, you should select someone who will respond to my questions. Otherwise, everybody thinks that somebody else responds, but I need time to time to have a feedback. Did you discuss equation of state of ideal Fermi and Bose gases in statistical mechanics courses?
We discussed equation of states. Yes, we did. But more in we did more in solid state physics, and then we discussed. We also discussed this in statistical mechanics. I think just in passing.
But do you know the tricks how to compute integrals with the Fermi distribution function?
Yes.
Namely, the derivative of the Fermi distribution function with respect to energy is a delta function. So, and then you proceed with a Taylor expansion. So, if at zero temperature you have a Fermi distribution function which is a step function, then the derivative of it is a delta function, because derivative of a step function is delta function, and so on and so forth. So you can Taylor expand and you can proceed with the calculations. Did you do this exercise? Because it's important. You need to be able to proceed with the calculations. If I ask you to compute entropy or compute specific heat, you need to be able to do it. Okay, I will still plan this exercise to refresh your knowledge of how to proceed with the calculations. If you feel that this is boring and you know everything by heart, tell me in advance. I will plan some other exercise about something which you don't know. Because even on the next lecture, we are going to definitely deviate from what you learn in statistical mechanics. Namely, in the next lecture, I'm going to discuss, first of all, paramagnetism. We will consider response of the Fermi gas to the magnetic field, taking into account first its spin degrees of freedom. This is Pauli paramagnetism, and second, orbital degrees of freedom. For the second part, I need to refresh with you quantum harmonic oscillator. We will introduce Landau levels. We will introduce density of states per Landau level, and we proceed with the calculation of thermodynamic potential omega and compute acceptability, both for paramagnetic and diamagnetic state. I doubt that you did it in statistical mechanics. Did you discuss Landau diamagnetism or not?
No, not Professor.
We did not.
Because it's lengthy calculation. It will take me 1 hour to proceed with the calculation of diamagnetic response. You need to take some Poisson summation, and there are some mathematics involved, but I go with you step by step, because this is very important. And all this discussion about effective mass and things are important in order to actually show you that some metals are diamagnetic, some metals are paramagnetic, and when we discuss superconductivity, we will see that superconductivity is ideal diamagnet. So magnetic field doesn't penetrate inside the superconductor. So it repels the magnetic field. The same way as diamagnetics do. They generate magnetic field inside, which tries to compensate external magnetic field. So this is how diamagnetism works. And diamagnetism and paramagnetism, and in principle any magnetism, is intrinsically quantum property. So there is no classical analog of magnetism. This is either related to quantum number of spin, which doesn't have a classical analog, or it's related to quantum oscillatory behavior and quantum oscillator quantization of levels in oscillator. And again, since quantization of level doesn't occur in classical mechanics, you will not get magnetism, diamagnetism in the classical system. Okay, can you follow me? Do you see on the blackboard what I write?
Okay.
I hope that next week this COVID team will meet, and maybe, since many of my colleagues insist that we need to restart in-person lecture, maybe, although I don't give you any promise, the COVID team will rediscuss it. I'm not saying reconsider, we will rediscuss it. So as soon as we get a permission from the COVID team, we resume in-person lectures, which will increase the level of interaction, of course.
Actually, for me, everything is not clear. I miss a lot of parts from Blackboard. Yeah.
Again, sorry, I have alternative to that. I can prepare a lecture with the slides, but believe me, with the slides, you will not be able to follow at all. Because with the slides, I can accommodate the content of 3-4 lectures in one lecture. So the density of information will be so high. So you will not be able to follow. When I write it on the blackboard, you can write it together with me. So you pass it through your mind, through your brain, and at least you follow me with the same speed as I do calculations. If I show you with the slides, we do it with the slides, believe me, it's going to be a disaster. One cannot do calculations with the slides. Here I can make step back, extend any line of calculation, put more details, put less details. With the slides, no way. So I understand that there is no perfect solution. I understand that we are all in a sort of tough situation. But so far I think that this lecture with the blackboard is the best what we can have so far. But I'm thinking to increase the level of interaction. Maybe we need to have a simple questions and answer session where I'm going to ask you questions and you send me your answer through Zoom, because I need to understand whether you follow me or you are completely lost. And I believe that some of you are following me and some of you are almost lost. This is a court, but this is unfortunately what we have now, and hopefully the situation will improve and hopefully we will be back to more or less normal life.
Sorry, Professor, I think it's time.
Yeah, please. I'm done. The lecture is finished. Goodbye.
Bye.
Bye. Thank you.